This is the perfect problem to prove to you that engineering is not just math. Normal and shear stress, this whole problem is just going to have one equation. Stress is force divided by area. Problem is, there's a million different areas in this problem. The engineering is figuring out which one is actually relevant based on how the piece could actually break. And there's a bunch of different ways it could break. The math at the end is going to be super simple, plugging in numbers, but the engineering is where most students get stuck. So we'll just go from top to bottom, A to B to C, and just figure out every possible way that this piece could break, and then find the relevant area for each of those methods. How could disk A break? There's really only one way, and that's just through regular normal compression due to the 140 kilonewton force, just pressing it, squeezing it. For normal stress, the relevant area will always be perpendicular to the force. So this is just the circular cross-sectional area of the top disk. And if I do all my unit conversions properly, which I did not, 140 kilonewtons should be 140,000 newtons. I end up solving for diameter 1 of 22.5 millimeters. And of course, this is a minimum diameter because if we made the diameter larger, then the 140,000 newtons would be spread out over a wider area, which would mean less stress, which would be safer. So a larger area is safer, so this diameter is a minimum. Come on back, buddy. You want to come back up? All right, now disk B in the middle, we're actually going to cover two different ways that this could fail. The first one is if A kind of pushed into it and compressed B. Again, this is called bearing stress. And this is why washers exist, right? Those metal rings, the purpose of a washer is to take a force from the head of a screw or a bolt and distribute it across a wider surface area, because a screw or bolt is really tiny, could really easily push into the wood or metal that it is attaching. By spreading it over a wider surface area, it's less likely to damage the thing it is fastening. But the good news for us right now is that this is actually exactly the same problem as we solved in part A. The force pushing in is the same 140 kilonewtons, and the area is still the same as the area of A. So actually the same diameter we found for A is the same diameter that would stop B from failing due to this same reason, since A and B are made of the same material. But now we're getting into something different. What if B failed in shear? This is punching shear. Just think of like a hole punch, like the office supplies. This is where instead of B being pressed inwards, just the entire undeformed disc just pushed all the way through, and you are left with a donut and a donut hole. In this case, the surface area that is affected is the outer surface area of that central slug. So the surface area of the round outer part of a cylinder is the circumference of the cylinder times the height of the cylinder. And so V over A, the same force that we used for N, is now also V. It was called N, a normal force, when it was perpendicular to the flat surface. Now it's called V, a shear force, because it's now parallel to that side surface, causing shear. And from this, we get a value of 17 millimeters for D1. Didn't we already solve for D1? How do we have two answers for this? Well, which one is right? Well, the answer is the minimum value for D1 is the larger value for D1, as weird as that sounds, and this is a super common mistake for students to make. So think about it this way. Pick a number right in the middle of 20. Would this object fail if we chose D1 of 20? And the answer is yes, it would. In part A, the minimum value was 22. It needed to be larger than 22 in order to not fail. So a value larger than 17 will make it so that B doesn't fail in shear. A value of 22 will make it so that both B doesn't fail in shear and A and B don't fail in compression. It needs to be higher than the highest minimum value. So our overall minimum value for D1 is the 22, so that both options will be safe above that level. All right, let's do this same punching shear example one more time to drive it home, but with part C. So suppose that B drives all the way through C, and again, just removes that whole slug of material from C. Again, V over A, the same force is everywhere, the same 140 kilonewtons pushing down and up, but the surface area now is going to be diameter 2, the circumference using diameter 2, and the height, that 10 millimeter thickness. We get a value now, D2, 35 millimeters, and a larger value for D2 would be okay, right? A larger diameter would mean more circumference, more surface area, so the force is spread out over more surface area. That would be safer. So this 35 is a minimum value. Larger values for D2 would also be okay. Next step, bearing stress for piece C. What if B, instead of punching through, just pushed through by compression? In this case, the surface area won't be the entire surface area of B because there's a hole in C. And we're trying to find out, how big can this hole be? The bigger the hole, the less surface area, which means there'll be more stress. So our area this time is going to be the area of a circle minus the area of the hole. So just pi r squared using D2 and then minus pi r squared using D3. This gives a value of 27.6 millimeters for D3, and this is going to be a maximum diameter. Because if the hole were smaller, that would be good. That would mean more surface area and safer. Larger diameters, bad. Less surface area, bigger hole, causes problems. My full mechanics materials playlist is linked down in the description. Go ahead and bookmark it now. You don't want to watch another video right now, probably. You got other stuff to do. But bookmark it, you can come back to it later. Have a great day. Good luck on your next test.